Hello, my name is Adam Huang from the Cognitive Science Department of Indiana University. This is a pre-recorded presentation for the 2022 International Conference on Cognitive Modeling about my recent publication, A Quantum Walk Framework for Multi-Alternative Decision-Making. I'll start with introducing models of multi-alternative decision-making in general, and then talk about a quantum walk model I constructed for multi-alternative decision-making. Traditionally, evidence accumulation process in human decision-making is modeled by the Markov random walk process. These Markov models focus on tackling the traditional context effects in human decision-making that includes similarity, attraction, and compromise effects. The plot on the right illustrates these context effects. However, there has also been abundant evidence showing violations of Markov assumptions in human decision-making. For example, the figure on the left shows that choice might interfere with confidence rating, which cannot be explained by any Markov model. One solution to the Markov violations is the quantum walk model. The quantum walk model is a quantum analogy of the Markov random walk model, which instead of working with probability transitions, work with probability amplitude transition. The amplitude transitions are more like waves propagating from state to state, while the Markov random walk model can be viewed as classical particles jumping from states to states. If you are familiar with the Markov random walk model, I compare the two models on the right analogously. For example, the Hamiltonian matrix in quantum dynamics is analogous with the intensity matrix of a continuous time Markov random walk model, and the quantum unitary is analogous with the transition matrix. Despite the quantum random walk model may solve Markov violations, it has only been applied to binary choice decision-making problem but not multi-alternative decision-making. This makes us wonder whether we can extend the quantum framework to also multi-alternative decision-making that can both address Markov violations and context effects. We come up with the multi-alternative quantum walk model. If you are familiar with quantum cognition, I compare the existing quantum walk model for binary choice with the new multi-alternative quantum walk model in the following table. In the binary case, we only need a single quantum state for the binary alternatives. The alternatives in the new model are now itself represented by a single quantum state, and a state that participates in the quantum walk is in some sense a joint state of these quantum states, which is lifted by a direct sum with attention rates. We'll discuss the Hamiltonian and the potential function in more detail in the next slide. Here, we describe how the Hamiltonian in the direct sum space is constructed. To model context effects, we employ this HMQ here to describe the interaction of evidence accumulation for alternative M on alternative Q, like these H11, H12, H13 on the left. In another word, thinking about alternative M might trigger or inhibit similar evidence of alternative Q, and this is modeled by this HMQ here. The HMQ are then direct summed for each M to HM, which is the H1, H2, H3 in the middle. The 3 HM in the diagram are then multiplied into the final Hamiltonian that describes the fluid dynamics. Note that since matrix multiplication is not commute, the order of presenting each alternative or thinking about each alternative matters for the final decision outcome. The potential function for HMQ are assumed to be linear, which is consistent with previous quantum walk literatures, and the diffusion rates are assumed to be constant. Finally, we illustrate the stopping conditions and how the model simulates. As seen from the plot, the two red lines here represent the stopping conditions. The horizontal line is for boundary or threshold-based stopping condition, and the vertical is for time pressure. The three alternatives are assumed to be independent such that simulating one alternative has no effect on the other. As you may see, the quantum walk model produced an oscillating mean confidence rating, while the Markov model produced monotonically increasing confidence rating, which makes them different. This is all I would like to present. Thank you so much for watching the video, and I'm looking forward to meeting you in the conference.